This is a review of shear and moment diagrams using a beam as an example structure that we'll be doing this on. So beams are flexural members which can resist three types of internal forces: axial, shear, and bending moments. Here's the beam that we're going to be analyzing. Okay, so we have our pin support, a roller support. Okay, the main span is 20 feet. There's a 6-foot cantilever on the right-hand side. Over the entire 26-foot length of this beam, it's supporting 2 kips per linear foot along the length of that beam. And in addition, there's a point load of 20 kips at the end of the cantilever. So given this loading, we're going to draw the shear and moment diagrams. Okay, so for the first step, we're going to be drawing the free body diagram, which we've shown here. Okay, so we have 2 reactions at the pin support, one vertical reaction, one horizontal reaction, and another reaction at the roller support on the right-hand side. Now notice we have 0 force for the reaction in the x direction, 12.2 kips vertical reaction, 59.8 kips vertical reaction. Okay, so we've already done 2 steps: draw the free body diagram, find the reactions. To get the reactions, you're going to be using statics. Sum of your forces in your x direction equals 0. Sum of your forces in the y direction equals 0. Sum of your moments about some point equal to 0. So that you should already know how to do. Okay, so what we're going to be doing to create our shear moment diagrams in the classic way of using equations. So because we have a point load or an abrupt change in the shear diagram, so point loads result in an abrupt change in the shear diagram, or the formula which expresses shear, as well as the formula for the moment. We need to create 2 equations, one for within this region, within this 20-foot span, and another set of equations for the cantilever span. Okay, so we're going to use method of sections, cutting one section here, and then later cutting another section here. So first, we're going to cut this section. So we're going to cut and isolate and create a new free body diagram. So if we cut it here and we use the remaining portion, we have our 12.2 kip reaction is still there, our 2 kips per foot along the length is still there, and we're going to define the length from the left-hand support to where we cut the section as this distance x. Okay, at that location, we're going to be putting in our internal force, which in this free body diagram we need to solve for. Okay, so V sub x, and it's important that we show this in the right direction. Okay, so V sub x is acting down. Now why is that? Well, on the first page of your handout I showed the sign conventions that are consistent with, and so what that means is that based on the loading direction, up, any force acting up being positive and any force acting down being negative, if you treat this loading diagram and then you create a formula with that sign convention, you can simply integrate to determine what the change in your shear diagram is going to be. But the formula for the loading diagram integrated will have a consistent sign convention with this type of positive shear and this type of positive bending moment. Okay, so when we cut our section, we have 2 unknowns, and usually when we have a free body diagram, we're free to choose whichever direction we want. But because we want to, in this method that we're demonstrating, we want to develop formulas for it, it's important for us to use a sign convention that's consistent with positive directions for shear as well as bending moment. So this is our sign convention, and you can see for our short element of a beam, a positive value of shear causes this type of deformation. And when we look on the right-hand side of that element, the shear reaction, or the internal force that's being replaced by the remainder of the beam that's not shown there, is pushing down on that element on that side, and on the left-hand side it's pushing up. So because we're cutting our section here and we're keeping everything on this side, then that means on the right-hand side of the portion that we're looking at, we're going to be drawing our shear reaction consistent with this sign convention, and that's why our shear reaction is shown acting down. Okay. Then same thing for our bending moment. So positive bending moment is if you have a positive attitude, you'll be smiling, so you can see that this beam is acting in a way that appears that it's smiling. So that's a positive bending moment. So again, on the right-hand side, you're going to have a counterclockwise moment being applied. On the left-hand side, a clockwise moment being applied. Okay, so this is going to be consistent. So it's not just that we're choosing this to be positive, but also this is consistent with a positive shear, consistent with positive and negative loading as well, which is on the first page of your handout. Okay, so here we've cut the section and we now have two unknowns and we're calling them Vx. You can think of this as shear as a function of x and our moment as a function of x as well. And so this is only going to be valid between x equal to 0, less than or equal to, or greater than or equal to 0, and x less than or equal to 20 feet. Okay, and so this equations we're going to develop are going to be true within this region. Okay, so now we have, this is that same figure. We're going to apply statics to it to solve for v of x and m of x. Okay, so some of our forces in our x direction, we're choosing up to be positive. We're going to set that equal to 0. Okay, so we have minus Vx, right, because Vx is pointing down opposite to our sign convention, plus 12.2 kips, that's our reaction here, which is shown acting up. And then we have minus 2, so minus, it's minus because the uniform load is acting in the down direction. So minus 2 times x, right, so this is kips per foot, this is forces, so it should be in terms of kips. The total area of this rectangle is 2 kips per foot, which is the vertical dimension times the length x. Okay, and so there are no other forces acting in the y direction, so we have that equal to 0. So if we are only unknown here, or what we're trying to determine anyway, is v of x, or our shear in terms of x. So that's going to be equal to minus 2x plus 12.2, and the units on this are kips. Okay, so we've solved for our shear, and so we want to solve for our bending moment. So we can go ahead and sum our moments, and notice we're summing our moments about point x. Okay, and right here, this red dot indicates this is the location that we're summing our moments. Now, the reason why we're doing it here is because in our moment equation, we'll eliminate Vx from the equation, because all of our moments are going to be whatever force acting at whatever distance is a moment, right? A moment is a force couple. And so Vx will not show up in the equation. That way we don't need to substitute this into the equation and make our math more complicated and have us have a greater chance for errors. Okay, so we'll go ahead and sum our moments about this point. So we have our 12.2 kips, it's acting up, which causes a clockwise rotation. Okay, so notice here we have counterclockwise is our positive sign convention. So counterclockwise acting is moments, and this we're just arbitrarily choosing for while we're doing our statics, summing our moments, setting them equal to 0. So 12.2 is causing a clockwise rotation, opposite to our sign convention for this formula. So that's going to be minus 12.2 kips times x, since it's x feet away. And then we're to that, we have our 2 kips per foot, which is acting down, causing a counterclockwise rotation. So that's positive 2. The magnitude of the equivalent force is 2 kips per foot times x. So 2x is our force. And the distance to the center of action of this is going to be half that distance, or half of x. So that's why our force 2x multiplied by the lever arm of x over 2. Okay, and then v sub x times 0, so that's not a term. And finally, we have our actual moment that we're solving for, counterclockwise rotation, consistent with our sign convention. So plus mx is equal to 0. Again, we're interested in what mx is along the length, so we're going to solve for that. So rearranging terms, we get 12.2x minus x squared. Okay, so this is our two formulas for our shear and moment diagram within that region. Okay, so what we can do to start to generate our shear moment diagrams is we're going to plug in our different values. So the values of interest are x equal to 0 and x equal to 20 feet. So for our shear diagrams, when x is equal to 0, we get 12.2 kips, and that's positive. So this is our shear diagram that we're developing. So far we know what this red dot is. We know that it's at 12.2 kips. Next, if we plug in x equal to 20 feet, in solving, we get minus 27.8 kips. So now we know this value here. Okay, we can recognize that our formula is in terms of x, not x squared. It has a -2 for the slope. So we could know intuitively, or from that we could just draw a straight line between these. And that's fine. Okay, so let's see what we know for our moment diagram by plugging in these values. So moment at x equal to 0. Okay, this is simply supported beam with no applied moment at the end. It should be 0 at the end because this is a pin roller. So if we plug in x equal to 0, we get 0 here and 0 there. So we're good to go. We know we're somewhere on the right track. That's a good thing to check yourself as you go through. Then we have our moment at x equal to 20 feet. Plugging in, we get minus 156 kip feet. So all that we know is this point and that point. Okay, and if we remember, we have an x squared term. Okay, our x squared term. It's negative, so you can think, okay, well, it's a parabola, and it's concave down, if you remember that. But I mean, we could easily draw a concave down like this. So how do we know that this is occurring? Okay, so that's going to be something you just have to guess and check, or kind of plug in the formula and find out. Okay, so next we're going to move on to the other section. So because of this point load, this is going to be an abrupt change or cause us to have to develop a new set of formulas for the region between x equal to 20 to 26 feet. Okay, so cutting a section here, okay, and then repeating the same thing where now we have the full 20-foot span plus an additional cantilevering section. Okay, we still have the 2 kips per foot along the length. We still have our 12.2 kip reaction. We now are including this 59.8 kip reaction in our formulas. Notice x is still defined from the same location as before, so all of these equations will have the same origin. It's important for us to know. Okay, and then again, we're cutting our section, and we're going to use our sign conventions. So the same that we did before. Vx, internal force, is going to be acting down. Mx, our internal moment, is going to be counterclockwise positive because both of these are on the right-hand side, and we're looking at our sign convention. Okay, so an important thing to know is x still is from this region to where we're cutting our section. And this dimension is going to be important for us as well. So it's going to be x, the total length, minus the 20-foot span. So that's what this dimension is, so that we can properly include this in our moment calculation. Okay, so again, we're applying statics. 12.2 kips causing a clockwise rotation. Summing our forces in the y direction, up being the positive direction, setting that equal to 0. 12.2 kips acting up. Okay, 2 kips per foot acting down. Okay, but that's not in terms of kips, so we need to find the area of this rectangle. So minus 2 kips per foot acting down multiplied by x. That's the total area under this distributed load. Okay, so again, we still have the same minus 2x term. This was the formula we created before. Okay, but now we have this 59.8 kips acting up, so that's positive. And finally, we have, again, as we did before, the minus Vx. So solving for it, we now have a new formula. Okay, so 72 kips minus 2 kips per foot times x. Okay, and so this is the term that changed, which is basically just a change related to this reaction. Okay, so for our moment diagram, again, we're going to sum our moments about the same location so that we eliminate Vx from our equation. Okay, counterclockwise is positive. We're going to set everything equal to 0. So again, this causes clockwise, so that's a minus 12.2x plus 2x, which is the force, 2 kips per foot, okay, times x. Now this is a positive 2x because this is acting down, causing a counterclockwise rotation, consistent with our sign convention. Again, the distance from the center of action of this force is from here to here, which is actually x over 2. So this is our force, that's our lever arm. And then we have 59.8 kips acting up, causing a clockwise rotation, okay, which is opposite of our sign convention for this formula. So minus 59.8 times the distance to that. So that's where this comes in. X times x minus 20 feet. Okay, and then finally, Vx times 0. so that's not included in the formula, and mx counterclockwise, consistent with our sign convention, so plus mx equal to 0. So again, we're interested in mx, solving for it. We get our parabola minus x squared plus 72x, and now we also have a constant as well. Okay, so like we did before, we'll plug in values at the boundary conditions, or at the locations where this formula applies. So plugging in x equal to 20 feet for our shear formula, okay, we end up getting 32 kips, so now we know this value. Plugging in x equal to 26 feet, we get 20 kips here, so we know this value. Again, we know this is a linear relationship, so we could draw a straight line between them. Notice that these are positive values as well. That's why they're up here. Okay, and we're only getting positive values because we're having consistent sign convention use when we're cutting our section and assigning Vx. If we drew it in the opposite direction, then these might show up in different locations. Okay, so for our moment formula, we plug in m equal to 20 feet. We should get the same answer that we did before because there's no applied moment here, okay, or no concentrated moment being applied at that location, so it shouldn't have an abrupt change on the moment diagram. Okay, so minus 20 squared. Okay, following through the equation, we get minus 156 kip feet, which is the same value we had before, so that's great. Okay, and then one more thing we have is, okay, plugging in x equal to 26 feet. Solving for it, we get 0 at the end of the beam with no externally applied moment, so we know, oh hey, we return back to where we were. But what we still haven't determined, although it's shown here, this is the answer, is all that we know are just these points. Okay, for the shear diagram, we know that it's linear, so maybe we're done with this, though we haven't solved for this yet. Okay, we know these are concave down formulas, but we don't know exactly where do they go. How do we know what they are? Okay, so what's important to figure out critical values is we're going to look at locations on the shear diagram where V is equal to 0. Okay, and we recognize, because this is a straight line, that there is some 0 point there. So we can say, okay, well, where is Vx equal to 0? We'll use our formula, minus 2x plus 12.2. This is the first one within this region. Set that equal to 0, solving for x, we get 6.1 feet. Okay, so you can do it that way. So then plugging in 6.1 feet into your moment equation, so when m is equal to 6.1 feet, that's using this formula, we get 37.2 kip feet. And so then we can figure out what this is. Now realize that the value on the shear diagram is 0. That means that's the slope on the moment diagram. Okay, that's why this becomes a critical point. So the value on the shear diagram is a slope on the moment diagram. Okay, and so we have these points, and if we use that philosophy, the value on the shear diagram is the slope of the moment diagram, we can actually fill in the rest of this curvature. So here, the value on the moment diagram here is a positive 12.2 kips, which means this is acting in the positive direction. Right? And over here, negative 27, so it has a negative slope on the moment diagram. Switches to 32, positive slope on the moment diagram, etc. Okay. So to summarize, this is our sign convention that we're using, and you saw that on the first page. So this is when we're developing those formulas, if we keep this sign convention while we develop shear and moment diagrams and using our loading diagrams, these will all be consistent. In fact, you can continue to integrate, divide this by EI, integrate it again to get rotation, integrate it one more time to get deflection, and it'll all be consistent with each other. Okay, and so here's just another example of doing a shear and moment diagram from our loading diagram. And this is to illustrate how you could do it graphically. Okay, so rather than creating a formula, why don't we just go ahead and use the fact that we're using integration and differentiation. These are all related as either integrals, integrating as we go down, or differentiating, taking derivatives as we go up of each of these formulas. Okay, so if we have a point load at the end of the beam, okay, 4 kips, this is our reaction, here's our other reaction. Based on that, we can see we have a 4-foot long beam, 2 kips per foot along half of the beam. 1 4 kip load, point load, 1 foot away from the end of the beam. This is what our deformed shape will look like. Okay, so this is our loading diagram, okay, our free body diagram, including the solved reactions. So we can actually just use these values. Okay, and anytime you have a point load, okay, that's a load in terms of kips. It's acting transverse to the member. That's going to be an abrupt change in shear. So let's go ahead and start to go from here to our shear diagram. So we can actually just take this abrupt change in shear and place it right on our shear diagram. Okay, so when we're off the beam, there's no shear. Then all of a sudden there's this reaction. So immediately, and this is acting in the up direction, positive sign convention. Okay, so we're going to have positive shear. Okay, so that's going to be consistent. So immediate change to 4 kips in shear acting up. Then we have 2 kips per foot acting down. That's negative. Okay, so because it's acting down, the value on the loading diagram is equal to the slope on the shear diagram. So the value is acting down. It's a minus 2 kips per foot. That means this slope here is minus 2 kips per foot. Okay, so the value on the loading diagram is the slope on the shear diagram. And so because this is a constant value, you're going to have a constant negative slope until you get to this location. Okay, and so the change in shear is going to be equal to the area under the loading diagram. So the area under this rectangle will be the total change in shear from there to there. So 2 kips per foot times 2 feet. Okay, that's 4 kips. So the change is going to go from 4 kips positive down to 0. Okay, so and then we can continue on. So the value on the shear diagram here is 0. So the slope is 0. And the change is the area under 0, which is 0. So there's going to be no change. Okay. Then all of a sudden we have a 4 kip point load. That's going to be an abrupt change in the shear diagram. So we can just take this load and draw it here. Okay, so we're starting at 0. We go to negative. Again, this is in the down direction. That's consistent with the negative sign convention, and these are consistent. So this is going to be acting down. Okay, and then again, the value on the loading diagram is equal to 0. So the slope on the shear diagram is also equal to 0. And then we can take our point load and immediately draw that as well. We get back to 0, and so we're good to go. Okay. Okay, so what we just did is we used these useful rules here. Okay. So the value on the load diagram is the slope of the shear diagram. Okay. And then the area under the load diagram is the change in shear. Okay, so this is just because the load diagram is the derivative of the shear diagram. That's why the load diagram is the slope, right? Derivative and slope. And the area under the load diagram is the change in shear. Okay, because we can integrate the load diagram to get the shear. Integration is finding the area under a curve. So the area under a load diagram is the change in shear. And notice we have a similar thing said from shear to moment. Okay, so we're going to do the exact same process. So these are a bunch of different ways of saying the same thing. So the value of the load diagram is equal to the slope of the shear diagram. The area under the load diagram is equal to the change in shear diagram. So from load to shear, shear to moment, we're going to do the same thing. And these are different critical locations that you'll want to check. Okay, so we can do that again. So the value of the shear diagram is equal to the slope of the loading diagram. So we have a positive 4 on our shear diagram, so that's going to mean that our moment diagram is going to have a positive 4 kip slope, which gradually decreases down to 0. So we know it starts out steep, and it's going to gradually decrease until it's horizontal or 0 at this location. So we can almost just draw this curve just by changing the slopes along the length. Okay, and so to figure out what that exact change is, we figure out the area under the shear diagram is equal to the change in moment. So the area of this triangle is 1/2 4 kips times 2 feet, or 4 kip feet. Okay, so the change from here to here is 4 kip feet. We've already got half of the moment diagram. Then the value on the shear diagram is 0. That means the slope on the moment diagram is 0. So we can just come straight across to here. Then the value on the shear diagram abruptly changes by 4 kips. It goes to a negative 4 kips. So that's why all of a sudden the slope abruptly changes to a negative 4 kips. Okay, then it's a constant slope all the way to the end of the beam, so that's a constant slope. So then all we got to do is figure out, well, what is the area under this shear diagram? Will tell us the change in the moment diagram. So 4 kips acting over 1 foot, and this is a negative area, right? Minus 4 kips times 1 foot, so the change is negative 4 kip feet. Okay, so again, we followed all these rules. Okay, we have then we have different critical locations that we may want to check. So the maximum shear usually occur at the reaction locations, the check locations of concentrated loads. Maximum moment usually occurs at zero shear, check locations of concentrated moments. Then we have positively changing shear diagram, concave up moment diagram, negatively changing shear diagram, concave down moment diagram. And concentrated loads usually will cause an abrupt change in the shear diagram, and concentrated moments lead to an abrupt change in the moment diagram. Okay, this last one can be a little bit tricky to figure out, but do some moment diagrams using everything else, and then see if you can't figure out how that makes sense. Okay, so here I want to show you what the same problem that we did, what the calculation process is. If we just use those rules and understand them, we'd never actually have to develop a formula. We can just do math. Okay, so this is the same beam that we did before where we cut sections, but these are the new calculations. Okay, so for our shear, we're going to start with zero shear, and then we have a reaction 12.2 kips, so we're going to put in 12.2 kips on our shear diagram. Then we know we have a negative 2 kips per foot. Okay, so we're starting here. We have negative 2 kips per foot acting down. That's the value of our loading diagram multiplied by the 20-foot span. And so we know that this slope is minus 2 kips per foot, and so we can just calculate what our next value is. So we get 12.2 kips minus, and this is the area, right? 2 kips per foot times 20 feet. Okay, and so we can immediately calculate what that is. Then next, we're at this point, okay, and we have a 59.8 kip reaction, so we're just going to draw that reaction there. So 59.8 kips plus the 27.8 kips that we were at is equal to 32 kips, so we get there right away. Then again, we know we have minus 2 kips per foot, so we start at the 32 kips minus 2 kips per foot times 6 feet to the end of the cantilever equals 20 kips, so we've drawn this location. And finally, we draw our point load on there, and we get back to 0, and we're good to go. So we've created our entire moment diagram extremely quickly. Okay, so now we're going to do our moment diagrams. Well, right away, we know at this support, we have a pin support. It's at the end of a beam, and there are no externally applied moments. Those are the 3 conditions you need to have to say that indeed the moment at the end of that beam is 0. Similar on this end, this beam is a cantilever. We're at the end of a cantilever, so there's no support there. There's no externally applied moments, so we know that the end here has to be moment equal to 0 because air can't support bending moment. Okay, so we know that's 0. Now here you may get confused because this is a roller support. So you may think, oh, roller, it allows rotation. That's true. But this beam is continuous over the support. So the support may not apply a bending moment to the beam or may not resist bending, but the beam itself has internal forces, and that internal force within the beam can be a bending moment. So beams resist bending moments internally, so there is potentially a bending moment existing on the moment diagram, and indeed there is. That's the largest bending moment that we have here. Okay, so we cannot say that the bending moment here is 0, only these 2. That's a common mistake people make. Okay, so but we want to figure out where are the critical points. We know that where shear is equal to 0, we can go ahead and figure out where that critical location is. And look at that. Instead of creating a whole formula, we know that this slope is in 2 kips per foot. We know this is 12.2 kips, so we can figure out what this is quite easily. We just take the 12.2 kips divided by 2 kips per foot. The units will come out in feet, so we got 6.1 feet. Okay, so you take the magnitude of the triangle divided by the slope, and you'll get the base of the triangle. Okay, so let's go ahead and move on. Let's figure out, well, we know we're at 0 moment at the end. We want to see, well, what's the maximum going to be? We know this is going to be a maximum. We also know that this is going to be a positive slope. Okay, so we'll start here. 12.2 kips is what we're starting at. Okay, which is, we're trying to find the area of this triangle. 12.2 kips times 6.1 feet divided by 2. The area of the triangle, that's going to be our bending moment at this location, and it's positive. Okay, so we know what that is. That's positive. Okay, and we also know that the value on the shear diagram is the slope of the moment diagram, so we know that that 0 value means we have a 0 slope here. So we're good to go there. And we also know that the value on the shear diagram here is a positive 12.2 kips, so it's going to have a positive slope. So you can almost just draw a line, and you know it's going to be changing. The slope is going to be getting smaller and smaller as you approach 0. So you can draw it concave down, and you'll know that intuitively. Okay, and similarly, at some point, we're going to get negative 12.2 kips. Okay, and that should occur because this is a common slope at another 6.1 feet away. Okay, so we can kind of draw this line, and we know that that's going to be symmetrical. And because this triangle will be symmetrical to the triangle that's at this location, minus 12.2 kips, they're the same triangle, just opposite sides. And then eventually, at the support, we're going to have an even steeper slope. So you can see with these 3 lines, just understanding how the slope changes, you can draw it concave down, and you know that it goes down below the 0 line all the way to here. Okay, because the area of a triangle that goes from here to here that has a magnitude 12.2 kips here, these are the same areas. The area is the change in the moment diagram. Okay, so we've drawn this moment diagram. We just want to figure out what that value is. So we start again where we were, 37.2 kips. We find the area of this shear diagram. It's a negative area, right? Minus 27.8 kips times the distance from here to here, which is 20 feet minus 6.1 feet. And it's a triangle, so divided by 2. So that's going to be the change in our moment. So we get minus 156 kip feet. Then again, all of a sudden we know that the slope abruptly changes because the value on the shear diagram abruptly changes. So we're here at a positive 32 kips. Okay, so our slope here is a positive 32 kips. And then we know here at the end we still have a positive 20 kip value at the end of the beam. So we know that the slope is non-zero, but the slope is less than it was. So here we can almost draw it again. Okay, and we already knew that the moment is equal to 0 because it's at the end of the beam. There's no externally applied moment, so we know it's going to be 0. So we can already draw this. And then the last step is just to check that indeed our formulas are right, or that we've done the shear diagram right by finding the area of this trapezoid and adding that area to the bending moment that we have. So we have minus 156 kip feet. The area of this is going to be the value of the high side of the trapezoid, 32 kips, plus the value of the low side, 20 kips divided by 2 because we're taking the average height, okay, multiplying it by the base, which is 6 feet. Okay, and so that all added, divided, and multiplied comes out to a positive 156 kip feet, and so we get back to 0, and we're good to go. Okay, so in your handout you have another example that you could use to work through if you want. And so I've drawn everything here to scale. Actually, in Word I drew it to scale this entire beam, so it's a little bit more complicated. And see if you can understand how to just graphically go from here to the shear diagram, and again from the shear diagram to the moment diagram. And just the things to note is that here when we're going from our loading diagram to our shear diagram, the values here are in brackets are the area under the load within this region. Okay, so we have 0 value times 5 feet, 0. 0 value times 10 feet is 0. Okay, minus 2 kips per foot times 10 feet is a minus 20 kips. So that's how that works. And then the value of the load diagram here, this is 2 kips per foot. It's down, it's minus, so I'm just saying the slope is that. Okay, so that's how you can kind of go through and check that you can do this. So again, taking the shear diagram, we're going to do the exact same thing we just did. So the area under shear is the change in moment. So the area under this 5 feet times 20 kips. Okay, positive is a positive 100 kip feet. The value here is 20. The slope here is 20. So similar for each of the other regions. Okay, well I think this covers the review of shear and moment diagrams, and you should be able to do this for any beam or structure that takes bending and shear.